Welcome to qnawire.
Here we're going to use Ampere's law to find the magnetic field at various distances from a cylinder carrying a current along its axis. And a reminder about Ampere's law. Basically, this law says that the projection of the magnetic field along a closed path is equal to mu naught times the current enclosed by that path. And oddly enough, Ampere's law is most useful if you actually don't need to do the integral on the left-hand side. And where you actually wind up doing the integral is on the right-hand side over a current density or current distribution inside your current-carrying object. But for a wire, the symmetrical path that you choose is a circle that surrounds the center of the cylinder or wire. And that's called an Amperian loop. And the projection of B along that loop is B times 2 pi r. And there are two such loops that you can draw a distance out r from the center. One is inside the wire, and the other is outside. And the difference between those is the amount of current that you enclose. So if you are outside the wire, what you do is you enclose the entire current that's enclosed in that cylinder. So let's put A in there. So we'll take this in two steps. We'll first find the magnetic field outside the wire with R greater than or equal to A. And so in that case, the I enclosed is the total integral over the current density with the cross-sectional area to the current. And here the cross-sectional area is the circular cross-section of the wire all the way out to A. The radius equals A. And of course, the current density is given to us. It is the exponential. So let's go ahead and put in that exponential. The differential cross-sectional area is r dr d theta, where theta is, of course, the polar angle that goes all the way around the circle. And since we have a radial symmetric current distribution, that will just give us 2 pi. And we need to put in the radial distribution, which is B. Let's put the constants out in front. So we know we don't have to integrate over a constant. 2 pi B. And then the current, let's see, there's a 1 over r that will cancel the r inside the integral. And I'm going to give the r inside the integral a prime on it, just so we distinguish it between the r in the integral versus the r on the left-hand side of Ampere's law. And we'll integrate over the whole circle inside the wire. Now this integral is not too hard to do. It may be a little bit easier if we make the substitution. U is r prime minus a over delta, and then du is dr prime over delta. So let's bring the delta over to the u side. And so this integral becomes the integral between u is minus a over delta up to 0 times delta e to the minus u du. And I don't want to hang out with all the details, but that probably gives you enough to see how that integral gets done. Integral of e to the minus u du. Here, let me just finish that out. So it gives us an exponential to evaluate between two limits. And now let's just kind of put it all together. The I enclosed is 2 pi b times the delta. And we have a minus 1 in the upper limit plus a e to the a over delta as the lower limit. And I'll be graphing this, so I want to evaluate it numerically and putting in all the numbers, the values. I'll just show some of the steps. Of course, 2 pi is always 2 pi. B is 600 amps per meter, and then 0.025 meters, and then e squared minus 1. And the units turn out good, 2 amps. So I'm getting something a little bit over 600 amps. Okay, so a nice numerical value. With that, we can see that B, so finally, we can put this together with the left-hand side. B times 2 pi r equals mu naught times I total. And mu naught is the permeability of free space. So that has a constant value of 4 pi times 10 to the minus 7 Tesla meters per amp. And we can finally simplify our magnetic field down. There'll be a constant out in front, 1.2 times 10 to the minus 4 over r. That will give us a magnetic field in Tesla as long as r is in meters. So let's use SI units. Okay, now we've done the hard work, but we now want to find the magnetic field inside where r is less than or equal to a. And in order to do that, again, the integral that we do is actually on the right-hand side, and it comes about from integrating that same current distribution, but instead of going all the way out to a, we're going to stop at arbitrary r. And we still have the j integrated against the area. The theta part comes out as 2 pi. And we've already kind of done the integral, so I'll leave out some of the steps because the integral looks the same as it did before, except for the limits. And what I get is the I enclosed is 2 pi b times delta. And here comes the integral with the two limits. we have, let's see, minus r over delta. And of course, we can check that out. If r is equal to a, we get e to the a over delta inside the parentheses minus 0, which should be what we got previously. Yes. Minus e to the 0 is 1. Okay, so it looks like it checks out. And now we can do a little bit of substitution. This part out in front. Looks like the same thing that's in I total with some exponential stuff divided out. Okay, so yeah, if you go back there and look, you just divide out the weird exponential part. And so our final I enclosed is going to look like kind of ugly, but we're going to numerically evaluate it. So not a big deal. Yeah, all these exponentials outside the parentheses, of course, just have numerical equivalents. And there's the functional form on the inside. So what we see is that the I enclosed is a fairly interesting function of R, we'll put it that way. And again, you want to put that in with the left-hand side of Ampere's law. And I won't write that out. You certainly just bring down the I enclosed. But now we want to put in numbers. And I'll spare you some of the algebra there. Putting in the numbers. We get basically 1.2 times 10 to the minus 4 over r times 1.16. And then the functional form as a function of r. And we can further simplify this down. Of course, b is going to be in Tesla if the r is in meters, not in centimeters. Okay, and so what does this look like, this magnetic field? I will drag up an Excel plot just to show you kind of what it looks like. It is finite at the origin. One can take the limit of that magnetic field as r approaches 0. And it has a nice finite value. Yeah, here's my graph. And interestingly enough, the magnetic field is the strongest at the center of the wire. And it just kind of nicely decays down from there. Looks almost like a smooth decay. And of course, the magnetic field should match up at the boundary of the cylinder. From the inside to the outside should be a continuous transition. And not only is it a continuous transition, but the functional form of the magnetic field looks to be very similar from inside to outside, even though the inside has an exponential form to it, whereas the outside is just a 1 over r type form. So interesting.